Dear students, in last class we studied impulse wave and the relevant definitions, and there we studied an expression for impulse wave also. For your reference, I have given that expression here once again, and we know that it has two exponential parts in it. To generate such a impulse wave, various circuits may be used which are called as wave shaping circuits. Here I have given 4 wave shaping circuits. You can refer, and these circuits are named as circuit A, circuit B, circuit C and circuit D. First circuit is RLC series circuit, and it is designed to have overdamping. Circuit B, C and D are having two RC circuits in them. To obtain impulse wave which is having two exponential parts in it, the initially charged capacitor C to a voltage of V is discharged into the wave shaping circuit by closing the switch S. Out of these 4 circuits, circuit A is used as model only. It is not used practically for generation of impulse waves, whereas circuit B, C and D are used commonly for generation of impulse waves in the laboratories. Reason for not using the first circuit for generation of impulse wave is it is having certain disadvantages. Those disadvantages are: wavefront time is controlled by R and L values, and wave tail time is controlled by R value only. That is, both front time and tail time are not independently controllable as R is common in them. The second disadvantage is the basic circuit gets altered when capacitive load is connected to the load terminals. Load terminals means the two terminals across which the output voltage V0 of T is measured. I will show you here. For the first circuit, these two will be load terminals. For the second circuit, these two will be load terminals. Similarly, for third circuit, these two will be load terminals, and for fourth circuit, these two will be the load terminals. You can see here, if capacitive load is connected, that capacitive load will be in parallel with R, and hence the circuit gets altered. But here, if we connect a capacitor across the load terminals, then capacitor will be in parallel with capacitor. So the total capacitance will be C1 plus 2. Hence the basic circuit will not get altered. Similarly, in circuit 3 and circuit 4. So because of these two disadvantages, RLC circuit, which is shown in figure A, is not used commonly for generation of impulse wave. Therefore, we will go to the analysis of circuit B directly. Now here you can see redrawn circuit B. When switch S is closed, in order to discharge capacitor C1, which is initially charged, let us say current I1 flows through R1 and current I2 flows through capacitor C2. Definitely the difference of these two currents will be flowing through R2. Let I1 be the instantaneous current through R1, I2 be the instantaneous current through C2. V be the initial voltage across C1. If switch is closed, here switch means yes, can write here yes as switch. To discharge initial charge on it, Then due to current I2 through C2, there will be V naught of T appearing across the C2, which is given by one by C2 into integration of I2 dt from 0 to T. If we take Laplace transform, we get V naught of S equal to one by C2S into I2 of S. Let us call this as equation 1. If we now apply current division rule or branch current formula to the junction here and write for current I2 in terms of I1 in Laplace domain, we get I2 of S equal to I1 of S into R2 divided by R2 plus 1 by C2S. Now let us call this as equation 2. We can calculate I1 of S as V by S into 1 by C1S plus R1 plus R2 into 1 by C2S by R2 plus 1 by C2S. Let us call this as equation 3. Substituting for I1 of S in I2 of S and then I2 of S in V naught of S, we get V naught of S equal to 1 by C2S into R2 divided by R2 plus 1 by C2S. Now here I will substitute for I1 of S, that is V by S into 1 upon one by C1 of S plus R1 plus R2 into 1 by C2S whole divided by R2 plus 1 by C2S. After simplification, and rearrangement, V naught of S will be equal to V by R1 C2 into the bracket 1 divided by S square plus inside the bracket 1 by C1 R1 plus 1 by C2 R2 plus 1 by C2 R1 into S plus 1 by C1 C2 R1 R2. Sum of roots of denominator alpha plus beta is equal to minus b by a, where b is coefficient of s term, a is coefficient of s square term, and c is constant. Product of roots of denominator alpha into beta is equal to c by a. Therefore, we get alpha plus beta equal to minus 1 by C1 R1 plus 1 by C2 R2 plus 1 by C2 R1, and alpha into beta, which is equal to C by A. C is 1 by C1 into C2 into R1 into R2, and the coefficient of S square, that is A, is equal to 1. Therefore, C by A will be equal to C only, that is 1 by C1 C2 R1 R2. These relationships between roots of equation and constant coefficients of S square S term is from your 10th standard studies. Taking inverse Laplace transform from V naught of S we get V naught of t as V by R1 C2 into the bracket alpha minus beta into e raised to minus alpha t minus e raised to minus beta t. I hope you all know how to take inverse Laplace transform because you have studied Laplace transforms and inverse Laplace transforms in your mathematics course. Usually 1 by R1 C1 and 1 by R2 C2 are much smaller in comparison with 1 by R1 C2. Hence, the roots may be approximated to alpha as 1 by R1 C2 and beta as 1 by R2 C1. So now here equation for V naught of t is having two exponential parts in it as discussed in the beginning, and now V divided by R1 C2 into the bracket alpha minus beta represents V naught. Front time is given by T1, that is equal to 3 times R1 into C1 C2 divided by C1 plus C2. If I call this C1 C2 divided by C1 plus C2 as C equivalent, then I can write T1 as 3 into R1 into C, where C is C1 C2 divided by C1 plus C2, and the tail time is given by T2 equal to 0.7 times R1 plus R2 and C1 plus C2 product. The formula for T1 and T2 discussed here hold good for circuits B to C. For circuit D, R2 is to be taken as 2 times R1 Dear students, in this lecture we have obtained an expression for output voltage of circuit B and the expressions for front time and tail time of circuits B to D. In the next class, we will take up multi-stage impulse generators, which are also called as Marx circuit, and after that we will solve some numericals related to the wave shaping networks. I will stop the class here and continue in next class. Thank you.